Hello all. Today's lecture will be about pool placement. Uh, in this lecture, we'll discuss a design method commonly called pool placement or pool assignment technique. In this technique, we assume that all state variables are measurable, can be measured, and available for feedback. If the system considered is completely state controllable, therefore, pools of closed loop system may be placed at any desired location by means of a state feedback through an appropriate state feedback gain matrix. The condition for a system to place the pools at certain locations is that the system must be completely state controllable. Then the pools of the closed loop system can be placed at any desired location by using the state feedback using a state feedback gain matrix. The present design techniques begin with a determination of the desired closed loop pools based on eigenvalues and eigenvectors from the transient response and or frequency response requirements such as speed, damping ratio, or bandwidth, as well as steady state requirements. By choosing an appropriate gain matrix for feedback, it is possible to force the system to have closed loop pools at the desired locations, provided that the original system is completely state controllable. Therefore, the design techniques used for the determination of the closed loop pools depends on the transient response or frequency response, such as response speed, damping ratio, zeta, or bandwidth, as well as steady state requirements, the requirements for the steady state error, and the steady state settling time. By choosing the appropriate gain matrix for the state feedback, it is possible to force the system to have closed loop pools at desired locations required by the system response or the frequency response of the system. And the original system must be completely state controllable for applying this method. We have a plant in state space given by x dot equals ax plus bu and y equals cx. X dot equals b times u plus ax. We integrate x dot, we get x. Then we multiply x by c to get y. This is a topology of the pool placement. The typical feedback control system, the output is fed back to the submission junction. For feedback, we feed the output back to the submission junction to compare it with the reference signal. It is now the topology of the design it changes. Instead of feeding back y, we are feeding back the state variables. The state variables are fed back. If each state variable is fed back to control input u, therefore, again ki, that would be n gains according to the size of the system, ki that could be adjusted. We can adjust these ki's to yield the required closed loop pools values. For the topology of the feedback through the gains, ki is represented by the feedback vector k capital. We have the states are fed back using the feedback vector k vector multiplied by negative. Then it is a feedback to the input compared with the reference, and then the input u is obtained. Now we get u as r minus kx. Then the equation of x dot equals ax plus b times r minus kx. We multiply b by the bracket. We get x dot equals ax plus br minus k bkx. We add the terms of the x, which is a minus bk times x plus br, and y equals cx. Then the new A matrix will be a minus bk. We will limit our discussion to single input, single output for simplicity. We will assume that the control signal u and the output signals y be scalars, scalar values, not vectors, and they are single input for u and single output for y. We also assume that the reference signal r is equal to 0. Then we reduce our signal to 0. We get a minus bk times x plus b R, for R equals 0, then x dot equals A minus Bx, Bk times x. And U equals negative Kx. From the block diagram of the system, U equals negative Kx. As the R reference signal is assumed to be 0. The stability of the transient response characteristics are determined using the new A matrix, which is A minus Bk. Their eigenvalues. If matrix K is chosen properly, eigenvalues of the system can be placed at any desired location. And the problem of placing the regulator poles, closed loop poles, at the desired location is called the pole placement problem. There are three approaches. We have three approaches that can be used to determine the gain matrix K to place the poles at desired locations. The first method is direct substitution method. Second method is the Ackermann's method or formula. The third method is using transformation matrix P. All these methods yield the same result. First of all, we will discuss direct substitution method. For the direct substitution method, we follow the steps shown below. First, we check the controllability of the system, if it is completely state controllable, by obtaining the controllability matrix B, AB, A square B, until A power n minus 1B, where n is the order of the system. If the system is state controllable, we define the state feedback gain matrix K equals K1 until Kn with the size of the system, which is n. Then we get the equation Si minus A plus Bk. A minus Bk is the alternative or the substitute for A for the from the last lecture for state space representation, with the desired characteristic equation obtained from the desired poles of the system S minus mu1 times S minus mu2 times S minus mu3, and equated with the determinant of Si minus La plus Bk, which is S power n plus E alpha 1 S power n minus 1 plus alpha 2 S power n minus 2 until alpha n minus 1 S plus alpha n. By equating the two equations, we get alpha 1, alpha 2, and alpha n minus 1 until alpha n. Now we consider the following. Example, consider the regulator system shown in the following figure. The plant is given by x1, x2, x3. Those are x dot. Then we put x1 dot, x1 dot, x2 dot, and I'm sorry, x2 dot, and last but not least, x3 dot equals A. This is the A matrix, and this is the B matrix. Okay, the system use the state feedback control U equals negative Kx, the desired eigenvalues, mu1 negative 2 plus J4, mu2 equal negative 2 plus minus J4, mu3 equal negative 10, determine the state feedback gain matrix K. First of all, we have to construct the controllability matrix and check system controllability. Controllability matrix will be equal to B, AB, A square B, which is as shown. Then we determine the rank of the matrix C by obtaining the determinant of the matrix C, which is equal to 3. Thus, the system is completely state controllable as the system controllability matrix is 4 rank. And arbitrarily pole placement is possible. We can place the poles at the desired locations. Then we assume the K matrix equals K1, K2, K3. Then we obtain Si minus La plus Bk. Si identity matrix is 3 by 3. S0, 0, 0, S0, 0, 0, S minus La 0, 1, 0, 0, 0, 1, negative 1, negative 5, negative 6, plus B 0, 0, 1, and K equals K1, K2, K3. we obtain the determinant of these matrices. First of all, we subtract S minus A and then multiply B times K and obtain the summation of the two. We obtain S cubed plus S6 plus K3 S squared plus 5 plus K2 times S plus 1 plus K2. The desired characteristic polynomial is obtained using the poles given or the eigenvalues given in the problem, which are -2 plus J4 and -2 minus J4 and -10. We multiply these three brackets S minus mu1, S minus mu2, S minus mu3 to obtain S cubed plus 14S squared plus 60S plus 200. Then we equate the coefficients from the previous equation and this equation. 1 plus k1 equals 200, then k1 equals 199. 60 equals 5 plus k2, then k2 equals 55. 14 equals 6 plus k3, then k3 equals 8. The second method is Ackermann method. First of all, we obtain the state controllability matrix and the check system controllability. If the system is controllable, we can proceed. Then we obtain the Ackermann formula, which is k equals 0, 0, zeros until 1, multiplied by the controllability matrix b, a, b, a square b until a power n minus 1 b, all inverse, times phi a, where phi a equals a power n plus alpha 1 a power n minus 1 plus alpha n minus 1 a plus alpha n times identity matrix. The same example we considered before, we now use the Ackermann formula to obtain the K matrix. Those are x1 dot, x2 dot, x3 dot. First of all, we check system controllability using the controllability matrix B, A, B, A square B, and check its rank by getting its determinant, which if it is not equal to 0, then the system is 4 rank, and the rank of the system here is 3. The system is completely state controllable, and the pole placement is possible. Then we obtain k equals 0, 0, 1. This system is third order, 0, 0, 1 times b, ab, a square b, all inverse, times phi of a. Phi of a equals a cubed plus alpha 1 a squared plus alpha 2 a plus alpha 3 I. Alpha I coefficients of the desired characteristic equation obtained from the characteristic polynomial. We subtract s minus pole 1 times s minus pole 2 times s minus pole 3, or the eigenvalues given in the example. S cubed plus 14s squared plus 60s plus 200. Then alpha 1 equals 14, alpha 2 equals 60, alpha 3 equals 200. We then obtain phi of a, which is a cubed plus 14a squared plus 60a plus 200i. First, a cubed plus 14a squared plus 60a plus 200i. We obtain phi a equals 199, 55, 8, negative 8, 159, 7, negative 7, negative 34, 170. Then we obtain the matrix K equals 0, 0, 1 times B, A, B, A square B. There is a B missing here. This is A square times B, all inverse, times phi of A. We obtain K equals 199, 55, and 8, which is K1, K2, and K3. This example is given to you for practice. Thank you for your time, and this is the end of the lecture. See you in the next lecture.